Hello, Berkeley CE admits. I'm Mark Stacy, Department Chair in Civil Environmental Engineering here at Berkeley. It's my great pleasure to congratulate you and welcome you to the incoming class of 2022. Berkeley is an amazing place to live and learn. You're going to get a world-class education here. And in Civil Environmental Engineering, I'm very proud of the collaborative and supportive environment that we create. Our courses have faculty who teach them regularly, and our faculty are very committed to that teaching. Our student competition teams and our student organizations are active and thriving and really form a strong community within CEE. Overall, I think it's a place you're going to find to be very supportive. I think you're going to find it a place where you can really thrive, taking advantage of all the resources that Berkeley brings, but in a supportive environment here in Civil Environmental Engineering. Again, welcome, congratulations. I hope to see you in the fall. And of course, go Bears.
Hello and welcome. My name is Cara Nelson. I am a professor in Civil Environmental Engineering with a focus on environmental engineering. For those of you that have been admitted to our program for next year, I want to start off by congratulating you. What a huge accomplishment. All of that hard work you've been putting in for so many years has finally paid off. So I want to give you a sense of what you could study in our program if you choose to focus on environmental engineering. What we study in environmental is how we can protect both our human populations and the environment. So how can we make sure that our water and our air are safe to support healthy human populations and also protect our essential ecosystems? We do this by drawing on basic sciences, so drawing on physics, chemistry, and biology to understand and describe sources of pollution in the environment. And then the engineering comes in because we help you gain skills to actually fix those problems. So all kinds of engineering problem-solving tools and design of technologies to either prevent or clean up pollution. I want to give you a specific example. I teach a class called Water Systems of the Future. So I'm going to share my screen now. This is a class that I developed with a co-instructor where we get to explore all kinds of fun topics and innovation on how we can redesign and rethink our urban water infrastructure that is so essential to supporting our human populations. Most of our water infrastructure was designed over 100 years ago. We're still using the same strategies that we started with over 100 years ago. And yet the problems that we're facing as a society are so much more complicated and pressing now. We are facing global climate change, we're facing rapid population growth, and in California, we're experiencing significant changes in our climate, especially drought, but more extreme weather events. So this has huge implications for how we can safely provide water to our human populations without destroying and causing further change in our environment. So I want to introduce you to the one water cycle. This is a new concept that illustrates that water is just water, and we can actually convert it between any usable form. We have the technology and know-how now to take water from the environment, but also take water that's been used by households, by businesses, by industries, and convert that back into usable form. And we can sort of design the treatment step to whatever its next use is, so we can tailor it. And not only that, but we can also recover all kinds of useful things, all kinds of resources from water that has already been used. So of course the water itself, but there's also the potential to harvest both energy that can feed into the energy grid, as well as nutrients that can be used as fertilizer. So one of the most extreme versions of this practice is sometimes unfavorably called toilet to tap. This is an exhibit at our one of our best local science museums, the Exploratorium, where there's literally my son drinking water out of a toilet. But this is a picture of myself drinking water that used to be wastewater that has been purified so that it's safe to consume it again as drinking water. And we call this potable water reuse. And the reason this is possible is because there are all these technologies. Here's an example treatment train now going from left to right that can be used in order to provide advanced treatment and purify wastewater back into drinking water. And this is the future in California. This is how we can provide a sustainable and resilient supply of water to our urban populations. And just to give you a sense of some of the science behind this, all those colored boxes in the bottom illustrate all the different types of treatment strategies that we can use to remove the chemical compounds and the pathogens that would be of human health concern from the water. So we are doing work that is absolutely essential for the advancement of humanity. And I'll just leave you with this inspiring quote from John Kennedy. I look forward to seeing you here in the fall.
Welcome to Cal Day. I'm Jonathan Bray, a faculty member in the Department of Civil and Environmental Engineering here at UC Berkeley. I'll talk a bit about geosystems engineering. Liquefaction is one of the effects that earthquakes can have on soil, and then it has that effect on buildings in terms of buildings tipping over, punching into the liquefied soil, sliding horizontally, even tall buildings tilting because of liquefaction in the foundation. So we care about buildings and we care about how the liquefaction affects the buildings. It's one thing when liquefaction takes your ride. It's another thing when it takes your throne. But being serious for a moment, liquefaction is not only an issue with buildings, but it affects your entire life in terms of it's a flood event. And what happened in Christchurch, New Zealand was not just the sand coming to the surface, but the water that actually flooded people's homes. Unfortunately, liquefaction can break pipelines such as gas pipelines and start fires. That's what happened in 1995 in Kobe, Japan. That's also what happened in the 1994 Northridge earthquake in Southern California and Los Angeles. And that's what also happened in '89 during the Loma Prieta earthquake with the fire that we had in the Marina District. I talked to some elderly people when I first came to the Berkeley area in the 1980s, and they talked about the great 1906 fire. It was an earthquake that struck the match, but what burned and destroyed the city was the fire. Liquefaction, and one of the evidence of liquefaction is not just the tilted buildings such as shown here in the 1964 Japan Nagata earthquake, but the ejecta, that you have water and sand, the water pressure builds up. So the earthquake shaking causes the water pressure, that's the water that's between the grains, to increase. Well, the grain to grain stresses are what gives soil its strength. And when you have the water pressure builds up, that grain to grain stress decreases, and that causes the strength to reduce. A little model is shown here. This is a small little building. I made a very loose sand. My earthquake is my hand just hitting this with a hammer, and you can see the devastating effect of liquefaction. But we can recognize when liquefaction is going to happen, and we can densify the soil by various techniques. And this is the same building, but the soil's been densified, and now the earthquake has no effect. Another important issue from non-earthquake side is actually landslides. They can occur during earthquakes, but they can occur during rainstorms. They can occur on a bright sunny day, as unfortunately happened in 2014 for the Oso landslide in the state of Washington, which killed 43 people. This is the run out of it in the photograph, as well as from a LiDAR study. The hot colors show ground that's been lost. And this is the area where ground is accumulated, which unfortunately buried people. This is what the landslide looked like in cross section. We have methods where we can look at how the material runs out It has momentum, so it moves across the landscape, and we can capture that. And that's a key aspect of doing hazard engineering. And it's important. For example, this is a tailings facility in Brazil that failed on a bright sunny day and killed over 200 people because of this kind of flow slide. So we need to understand why the flow slide initiated, but we also need to understand how far it's going to run out. I don't want to leave you with just a devastating effect of soil engineering. So I think, as much as humans build beautiful things, I think nature has built the most incredible thing in terms of soil. These are actual pictures with a scan electron microscope of images from Guayaquil, Ecuador, on a project I worked in. And I challenge you to find something as beautiful as this, which looks like the Leaning Tower of Pisa, or this part of soil. So soil has beauty, but it also could be precarious if it loses its strength and stiffness. And so that's why we do the civil engineering assessment of soil and its effects on structures. Thank you very much.
Hi, I'm Tracy Becker. I'm an associate professor in civil and environmental engineering here at UC Berkeley. I personally do a lot of research in the areas of structural engineering, and I'm really focusing on how bridges, buildings, even energy systems like solar panels or nuclear power plants perform under loads like wind or earthquake. A lot of focus on earthquake here. So I'm here in the second floor lab in Davis Hall, and there's lots to see and lots going on. If you are interested in joining the undergrad concrete canoe team or the undergrad steel bridge team, you would definitely spend lots of time down here, because this is where both teams do most of their physical work, the building and setup. So we also do a lot of experiments here for our research. And so here's one of the setups that my graduate students have been using recently. What you can see is an isolation bearing. This is a rubber bearing, and this is a special bearing. It looks pretty boring, but what this is because it's rubber, it can displace as far as it is tall. So really, really flexible system. And a lot of times we think that we need to make buildings and bridges really strong, really stiff in order to perform really well in an earthquake. But what that can do is actually make your building almost like a milkshake, because it's so stiff, it has large accelerations, it shakes up quite a bit. So what actually can be better is to have a more flexible system. So we use these isolation bearings to sort of decouple the behavior of the building or bridge from the ground in an earthquake. So this test is actually for the Coronado Bridge, and we are testing the isolation system that's at the top of the piers of the bridges. Now you're going to say, this doesn't look like a bridge. That's because this is a special kind of test called a hybrid simulation. And in the hybrid simulation, we physically test one component and we numerically simulate the rest of the bridge. So that means we have a computer model of the rest of the bridge. So every time step in this experiment, we have to do a numerical model that has to tell us the demands on the bearing, and the bearing has to tell us back what the demands are on the numerical model. So they're continuously talking to each other. This is the hydraulic jack that pushes and pulls the bearing. So not only does this test require in-depth knowledge of how the structure is going to behave, so good structural engineering, also requires a lot of understanding of control systems to control this well, so we don't have poor feedback. And so that's some mechanical engineering knowledge. It also requires that we have good communication between all of the computers that it takes to send and receive these signals and talk properly. So it also requires some computer science knowledge. So it's a huge interdisciplinary field to do these hybrid simulations. In this lab, we do all sorts of testing. We do lots of work with Caltrans, looking at bridge piers, as well as so for arch bridges or for walls. Lots of systems like that. We do work for EB mud. We do lots and lots of different types of testing. All of these pieces are reconfigurable. last fall we had a huge wall about 40 feet long all the way down the edge of the lab. It was an amazing test, and I've never seen anything like it. So I hope you come and join us to see all the fun things we do in the second floor of Davis Hall.